Welcome to Data Science 1, Probability, Properties and Probabilities. So, quick review last time. We talked about sample spaces. We know what events are. We know how to come up with the probability of E, both empirically and if we had the equally likely approach. And we noticed that this can be time consuming. One, we have to know how to count, and one, we have to do the experiment. But right now, we need to back up a bit. We need to start thinking about what probability really means and how it behaves. So that's what we're going to talk about here. We're really not going to do any sort of problem or example. Just want to think about it. So if we think back, we can think of S as being a box here, and it contains all the possible outcomes of our experiment. And then what we could do is we can think of this circle here as the event that we're interested in. And we're going to put all the outcomes in our sample space that correspond to that event inside this circle. So this circle represents the event that has occurred. Okay, it's very, very simple. Now, if we have two events, we could put all the events that correspond to E into the circle for E, and all the events that correspond to the event F, or all the outcomes that correspond to the event F, inside the circle for F. Pretty simple, just the same as before. Now, what we might want to do is see what happens if we overlap these things. Well, if we overlap these two events, E and F, then where they overlap, this section here in the middle, okay, is called the intersection, okay, of E and F. And we denote it with this upside down U. Okay, this stands for E intersect F, and it's what the two events have in common. So often we'll have more than one event, and sometimes they'll have something in common. And we'll talk about this more as we go along. But first we need to sort of establish the idea. It's what they have in common. Now, here we have two events here. And if I look at the intersection, they don't overlap at all. So E intersect F is equal to the symbol here, which is an from, I think, Danish. And it's a zero with the line through it, and it means that they don't overlap. They have nothing in common. It's the empty set. Now, what happens if they overlap, and we're interested in whether it is an E or F? We don't care whether it's in both. We just care, is it an E or is it an F? And in that case, this is a different idea than being an E and F. Okay, so here this would be, we don't care really where it is. It's somewhere inside of this shaded region. This would be considered the union. And it's different than the intersection because we're sort of lumping the two sets together. We're saying it's E and it's F, but we don't want to overcount things. So this is how we would denote this. All right, here's another idea. What about if we have this event E and we're interested in everything that's not E, okay? So we have this event E, and we want to know, well, what else could have happened? And everything else that could have happened. This is the idea of a complement. It's everything else that could have happened that's not inside of E, okay? So it's everything else. When you hear the complement, it's everything else in this case. All right, so probability is based off of three axioms that are going to hold these things together, and that's the reason we talked about these ideas from the Venn diagram. And we'll keep recycling back to these ideas as we go along. But they're pretty easy to think about here. The probability of an event is greater than or equal to 0, which means that's not going to be negative. That should be relatively easy to sort of absorb. Okay, the probability of S equals 1. Okay, it says if I conduct the experiment, one of the outcomes in S will happen. Okay, so that means if I conduct the experiment, one of the outcomes will happen. The one means it's kind of like 100%. Everything is in the sample space. And then we have this other idea down here that says if we have a whole bunch of events, E1, E2, E3, and they can keep going in S such that they are all disjoint from each other. So if I take the intersection of any of them, that they don't overlap, okay, then if I want to come up with the union, the combination of the events, it's simply get to add them together. Okay, so this just get to add the probabilities of each of the events together, and this is pretty easy. Now, when you see 3, most people go, oh, I have no idea what this means. But the idea here is really, really simple, and it's an idea that you already know, okay? That means probability behaves like area. If you've ever done anything with area, painted or whatever, okay? Right? You can't have a negative area. That doesn't make sense because I have to put a positive amount of paint on the area, okay? It means that here we have all of the area is equal to 1, and that if we can break things up in a certain way, we can find the total area by just simply adding the areas together. And as we go along, we'll keep seeing this idea. But these are the basic ideas or properties of probability that we're going to need as we go forward, and I'll keep referring back to them. So right now, if you feel a little uncomfortable with them, that's fine. We're going to keep going, and you'll see how these come into play later. All right, so knowing that probability behaves like area gives us a way to think about the topic using ideas already know. Okay, so we'll need a few more rules that will help us out. Drawing a Venn diagram can often help you solve the problems. And thinking about problems as area of the event in the Venn diagram, with the total area of the Venn diagram being 1, really will help you solve some of these problems. And we'll start looking at some of these problems in the next video. See you there.